We built a machine to stare directly into the face of creation, hoping to find answers. But instead, we found a paradox that threatens to dismantle our understanding of reality. The James Webb Space Telescope was launched as humanity's greatest eye, a golden mirror designed to peer back to the very first moments of light in the universe. We expected to see the chaotic, dim sparks of infant galaxies struggling to form in the primordial soup of the early cosmos, barely holding themselves together against the dark. Instead, the data streaming back to Earth revealed fully formed monsters, massive galaxies glowing with the intensity of billions of suns where only darkness should have been. Imagine walking into a nursery and finding a fully grown adult waiting for you. That is the violation of natural law that astronomers are currently staring at in horror. These celestial objects are too big, too bright, and far too old to exist in the time frame that our physics allows, suggesting that the timeline of the universe is a lie. This is not just a rounding error or a glitch in the sensors. This is a fundamental crack in the foundation of the standard model of cosmology. For decades, we believed we knew how the universe began, how gravity slowly pulled dust together to form the first stars over hundreds of millions of years. But the images from deep space show organized structure and immense mass mere moments after the Big Bang, shattering every simulation we have ever run. If these galaxies exist, then our understanding of gravity, dark matter, or even the age of the universe itself is catastrophically wrong. The implications are terrifying because if we are wrong about the beginning, we cannot possibly predict the end, and we are drifting in a cosmos we do not understand. Michio Kaku and other leading physicists are looking at the data with a growing sense of unease, realizing that the textbooks may need to be burned. The objects in question, red pinpricks of light from the dawn of time, contain more mass than should have been available in the entire universe at that specific moment. It is as if someone placed a starship in the Stone Age. The materials, the time, and the physics simply were not there to build these structures. We call them universe breakers, a collection of 6 galaxies that appear roughly 500 to 700 million years after the Big Bang, yet look as mature as our own Milky Way. According to the Lambda CDM model, which has ruled science for decades, gas clouds should have still been cooling, not forming majestic spiral arms. The density of these galaxies suggests that 100% of the available gas turned into stars instantly, a process that is physically impossible in our current reality. This efficiency defies the laws of thermodynamics and stellar formation, leading some to whisper that the Big Bang might not have happened when we think it did. Could the universe be twice as old as we measured? Or are we looking at the remnants of a previous universe that survived the reset? The telescope that was meant to be a tool of discovery has become a harbinger of confusion, plunging modern astrophysics into a desperate crisis. Every time we point this golden mirror at a patch of dark sky, we find more anomalies that refuse to fit into the boxes we have built for them. The light from these ancient galaxies has traveled for over 13 billion years to reach us, carrying a message that says, "You are wrong about everything." Scientists are frantically recalibrating the redshift calculations, hoping that this is a mistake, a calibration error, anything to save the standard model. But the data is robust, the instruments are precise, and the reality is staring us in the face. The early universe was a crowded, bright, and impossible place. If gravity behaved differently back then, it means the fundamental constants of nature are not constant at all, but shifting variables that could change again. This instability suggests that the ground beneath our feet, atomically speaking, is not as solid as we believe, subject to cosmic changes we cannot predict. We are like ants trying to understand the architecture of a skyscraper by looking at a single grain of sand, and we have just realized the sand is fake. The impossible galaxies are roughly 10 times larger than anything our simulations predicted could exist at that epoch of cosmic history. To create such mass, stars would have had to form at a rate that violates the Eddington limit, the maximum brightness a star can achieve before blowing itself apart. So either these stars found a way to bypass the laws of physics, or they are not stars at all, but something far more exotic and dangerous. Some theorists speculate these could be dark stars, massive giants, powered by the annihilation of dark matter rather than nuclear fusion. If dark stars exist, they would be millions of times brighter than our sun and could explain the impossible data without breaking the age of the universe. However, the existence of dark stars would imply that dark matter is a tangible fuel source, capable of burning, which changes the entire energy equation of the cosmos. Another theory suggests we are seeing quote, primordial black holes masquerading as galaxies, eating gas so furiously they mimic the light of billions of stars. If the early universe was filled with supermassive black holes, then the seeds of destruction were sown before the first planets were even born. This challenges the very safety of our galaxy, suggesting that supermassive singularities are far more common and formed far earlier than we ever dared to imagine. The Hubble telescope hinted at this tension, but James Webb has screamed it into the void. The numbers do not add up. We are currently living through a scientific revolution comparable to when we realized the Earth was not the center of the solar system. But this time, we are being displaced from time itself, forced to admit that we have no idea how long the play has been running before we enter the stage. The deeper we look, the more the universe looks like a constructed puzzle rather than a natural evolution, a thought that haunts many astronomers. Professor Joel Leha stated clearly, "We just discovered the impossible," acknowledging that these findings require a total rewrite of cosmology. There is a palpable fear that we have hit the limit of human comprehension, that the universe is too complex for our primate brains to model. But we cannot look away, because these anomalies might hold the key to our ultimate fate, to the eventual collapse or freeze of everything we know. If the expansion rate is different than we thought, the big rip might come sooner, tearing apart the atoms in your body in a cosmic instant. We are not just observing history. We are observing the mechanics of a machine that includes us as a very small, disposable gear. The James Webb Telescope is peering through the keyhole of a locked door, and something on the other side is blocking the light. We are seeing galaxies that are stable when they should be chaotic, massive when they should be tiny, and red when they should be blue. The crisis in cosmology is no longer a polite debate at conferences. It is an emergency siren ringing in every observatory on Earth. We must now dive into the darkness of these findings and reconstruct the history of the universe from the ashes of our old theories. Prepare yourself, because the reality you thought you inhabited has just been disproven, and what replaces it is far stranger and far more terrifying. To understand why the panic among astrophysicists is so genuine, we must first look at the cathedral we built to worship the cosmos, the Lambda CDM model. For over 40 years, this has been the standard model of Big Bang cosmology, a mathematical framework that seemed to explain everything from the cosmic microwave background radiation to the large-scale distribution of galaxy clusters. It was elegant, precise, and comforting because it provided a timeline that made sense. It told us that the universe began in a hot, dense state, expanded rapidly, and then cooled. It told us that gravity is a patient artist, slowly sculpting order out of chaos over billions of years. According to this model, the early universe was a soup of particles that took hundreds of millions of years to coalesce into the first stars, and billions of years to form massive galaxies. Lambda CDM was our map of reality, the bedrock upon which all modern astronomy was built. But the data from the James Webb Space Telescope has acted like an earthquake, cracking the foundation of this cathedral, and suggesting that our map is not just slightly off, but fundamentally incorrect. We trusted this model because it worked for the local universe, but as we peer back into the deep past, we are finding that the rules we thought were universal might be temporary, local, or entirely fictional. The era we are investigating is known as the Cosmic Dark Ages, a period of profound silence and blackness that existed before the first stars ignited. In the standard timeline, after the Big Bang, the universe was a hot fog of plasma. As it expanded, it cooled, allowing protons and electrons to combine into neutral hydrogen atoms. This released the light we see today as the cosmic microwave background. But after that flash, the universe went dark. There were no stars, no galaxies, no sources of light, only vast, invisible clouds of hydrogen gas and dark matter drifting in the void. This period was supposed to last for hundreds of millions of years. It was a time of gestation, a slow, cold slumber where gravity worked imperceptibly to pull matter together. The models predicted that structure formation during this time was inefficient and sluggish. We expected the Dark Ages to end gradually, with small, fragile protostars flickering into existence one by one, struggling against the darkness. But the new data suggests the lights turned on all at once, in a violent, unexplained explosion of structure that skipped the gestation period entirely. It is as if a child was born and immediately stood up to speak in full sentences. The mechanism we thought governed this era is called hierarchical clustering, a fancy term for a bottom-up construction process. Imagine building a city with Lego bricks. You start by snapping 2 bricks together, then 4, then 8. Slowly you build a house, then a street, and eventually, over a long period, a skyscraper. This is how galaxies are supposed to form. Small clumps of gas merge to form star clusters. Star clusters merge to form dwarf galaxies. Dwarf galaxies merge over billions of years to form massive spirals like the Milky Way. This process is governed by the speed of gravity, which is a weak force. It takes time for gravity to pull distant objects together. Therefore, finding a massive galaxy with a defined shape and billions of stars less than 500 million years after the Big Bang is physically impossible under this model. It is like finding a fully constructed skyscraper on the ground 5 minutes after the first brick was manufactured. The timeline does not allow for the necessary mergers to have happened. The existence of these galaxies implies that either gravity was much stronger in the past, or the universe started with the skyscrapers already built, a concept that terrifies scientists because it implies fine-tuning, or a pre-existing structure we cannot explain. When we launched the James Webb Space Telescope, the expectation was managed carefully. We were told we would see faint red smudges, the messy, chaotic infants of the galaxy family. Hubble had taken us to the edge of the cliff, seeing back to about 400 million years after the Big Bang, but its vision was blurry and the infrared spectrum needed to see that far back. Webb was designed to see clearly into that epoch. The astronomers had prepared their papers, ready to confirm the lambda CDM model by documenting the slow, clumsy birth of the first galaxies. They expected to see low-mass, irregular blobs of gas with very few heavy elements. They expected to see a universe that looked like a construction site, full of raw materials and very little finished product. Instead, the very first deep field images returned objects that looked shockingly normal. They were symmetrical, they were dense, they were bright. They looked like they had been evolving for billions of years, not millions. The cognitive dissonance was immediate. It wasn't just that we found one anomaly. It was that the entire population of the early universe looked different than our simulations. It was like sailing to a new continent expected to be uninhabited wilderness, and finding a bustling, advanced metropolis waiting for you on the shore. Let's talk about the specific universe breakers identified by the CEERS survey and other deep field observations. These 6 galaxies, identified in data analyzed by Ivo Labe and his team, possessed masses as high as 100 billion times that of our Sun. To put that in perspective, our Milky Way is about that massive, but it took over 13 billion years to accumulate that weight through countless mergers and accretion events. These new galaxies achieved that same mass when the universe was only 3% of its current age. If you do the math, and believe me, thousands of physicists have checked the math, it requires these galaxies to turn almost 100% of their available gas into stars instantly. In the local universe, star formation is an inefficient process. Only about 10 to 20% of gas in a cloud actually collapses into stars. The rest is blown away by stellar winds and supernovae. For these ancient galaxies to exist, they would have needed to operate at near 100% efficiency, violating the feedback loops that regulate star formation. It's like pouring a gallon of gasoline into a car and having every single molecule convert perfectly into motion with zero heat loss. It defies the laws of thermodynamics as we understand them in astrophysical contexts. The crisis hinges on a measurement called redshift, denoted by the letter Z. As the universe expands, it stretches the fabric of space-time, and the light traveling through it gets stretched as well. Blue light stretches into red light, and eventually into infrared. The higher the Z number, the older and more distant the object. Before Webb, a redshift of Z equals 10 was the holy grail, a theoretical limit where we expected to see only the faintest sparks of creation. Webb has routinely found candidates at Z equals 11, Z equals 1,3, and even higher. A redshift of 13 corresponds to just 330 million years after the Big Bang. At this point in time, the universe should have been thick, with neutral hydrogen fog, making it opaque and difficult for light to escape. Yet, we are seeing bright, luminous sources that seem to have punched a hole through the fog with ease. The light from these objects is so shifted that it is moved entirely out of the visible spectrum, invisible to human eyes and invisible to Hubble. Only Webb's gold-plated beryllium mirrors, kept at cryogenic temperatures, could catch these ancient photons. And the story these photons are telling is that the universe woke up much faster and much more violently than we ever dreamed. When the data first arrived, the immediate reaction was denial. This is a standard phase in the scientific method. The instrument must be broken. Astronomers desperately hoped that the calibration of the telescope was off. Perhaps the models of the detectors were wrong. Perhaps what looked like high redshift galaxies were actually low redshift galaxies that were just very dusty and red. Dust can mimic the redshift effect by absorbing blue light and letting red light pass. This was the dusty imposter theory. It was a comforting safety raft. If these were just dusty, nearby galaxies, then the standard model was safe. The textbooks wouldn't have to be rewritten. We wouldn't have to tell the public that we don't know how the universe began. For months, papers were written arguing that the calibration was the issue, but then came the spectroscopy. Spectroscopy doesn't lie. It breaks the light down into a fingerprint of chemical elements. And when Webb finally pointed its spectrograph at these targets, the safety raft sank. The spectroscopic confirmation proved that many of these galaxies really are that far away. They are truly ancient, and they are truly massive. The denial phase is over. Now the panic begins. The implications of this mass discrepancy are chilling because they touch upon the nature of dark matter. In the standard model, every galaxy forms inside a halo of dark matter. This invisible scaffolding provides the gravity necessary to hold the gas together so it can collapse into stars. The size of the galaxy is strictly limited by the size of the dark matter halo. You cannot have more baryonic matter, normal stuff like stars and gas, than the dark matter halo can support. But these early galaxies are so massive that they appear to contain more normal matter than the dark matter halos of that time could gravitationally hold. This is the baryon catastrophe. It suggests that either dark matter behaves completely differently in the early universe, or that these galaxies formed without dark matter at all, which should be impossible. If they formed without dark matter, then what held them together? What force prevented them from flying apart? We are staring at structures that seem to defy the gravitational logic that holds our own solar system together. It opens the door to alternative theories of gravity, like MOND, modified Newtonian dynamics, which have been ridiculed for decades but are now looking uncomfortably plausible. Let's go deeper into the impossible brightness. The luminosity of these objects is off the charts. In astronomy, luminosity is a proxy for mass. We count the light to estimate how many stars are there, but what if we are misinterpreting the light? There is a terrifying possibility that these are not galaxies filled with billions of normal stars, but rather objects dominated by top-heavy star formation. In the modern universe, most new stars are small red dwarfs, which are dim and live forever. But perhaps in the early universe, the conditions favored the creation of only massive, blue monster stars, stars thousands of times the mass of the Sun. These stars would burn brilliantly and die young, detonating in hypernovae. A galaxy made entirely of these monsters would be incredibly bright, but would weigh less, potentially solving the mass problem. However, this solution creates a new nightmare, a universe filled with constantly exploding nuclear bombs, sterilizing space with gamma-ray bursts, making the formation of life or stable chemistry impossible for eons. It paints a picture of the early cosmos not as a nursery but as a violent, radioactive hellscape where stability was the exception, not the rule. Another contender for the truth is even darker: the little red dots. As astronomers zoomed in on these high redshift anomalies, they found that many weren't spread-out galaxies, but compact point sources. This suggests that we might be looking at quasars, supermassive black holes actively feeding on gas. If these universe breakers are actually black holes, it solves the mass problem, because black holes are incredibly efficient at converting matter into light, energy, through their accretion disks. A relatively small amount of matter falling into a black hole can outshine an entire galaxy of stars. But this solution forces us to ask, how did supermassive black holes form so quickly? To get a black hole of a billion solar masses that early you need a seed black hole that is already huge. But where did the seed come from? Standard stellar collapse creates black holes only 10 to 100 times the mass of the Sun. To jump from 10 to 1 billion in such a short time is mathematically impossible via normal feeding rates. This leads to the theory of direct collapse black holes, clouds of gas so massive they didn't even bother forming stars. They just collapsed directly into a singularity. A hole in reality that opened up simply because there was too much matter in one place. The concept of direct collapse black holes is the stuff of cosmic horror. It implies that in the early universe, entire regions of space could just fail under their own weight, vanishing into a singularity without warning. No supernova, no beautiful explosion, just a sudden, catastrophic implosion into darkness. If this process was common, the early universe was a minefield of collapsing space-time. These direct collapse seeds would then act as anchors, pulling in everything around them, growing at exponential rates. This would explain the brightness we see. It's the death scream of matter falling into these primordial maws. But it also implies that the seeds of our galaxy's destruction are woven into its very core. Every massive galaxy, including the Milky Way, orbits a supermassive black hole. If these monsters were born from direct collapse, they are the ancient rulers of the universe, and we are merely the debris orbiting their dinner tables. It shifts our perspective from galaxies are collections of stars to galaxies are feeding troughs for central singularities. We are not the purpose of the galaxy. We are the byproduct of a black hole's growth cycle. Let us consider the Eddington limit, a strict speed limit imposed by physics on how fast a black hole can eat. As matter falls in, it heats up and glows. This light creates outward pressure. If a black hole eats too fast, the light it generates pushes the food away, starving it. This self-regulating mechanism is what prevents black holes from consuming the entire universe instantly. But to explain the monsters Webb is seeing, they must have broken the Eddington limit. They must be super Eddington eaters, consuming matter faster than physics should allow. How? We don't know. Maybe they have magnetic fields that funnel gas in faster than light pressure can push it out. Maybe the laws of radiation pressure were different back then. Or maybe, just maybe, our understanding of the relationship between light and gravity is flawed. If black holes can eat without limit, then they are far more dangerous than we believed. It means they can grow from a speck to a galaxy eater in the blink of a cosmic eye. It renders the universe a much more predatory place, where the monsters are not constrained by the table manners of physics. The confusion has reached such a fever pitch that some scientists are revisiting a theory that was laughed out of the room decades ago. Tired light. This theory suggests that the universe isn't expanding at all. Instead, light just gets tired and loses energy as it travels through space, shifting to red. If this were true, the Big Bang never happened. The universe would be eternal, infinite, and static. While this theory contradicts mountains of other evidence, like the cosmic microwave background, the fact that it is being whispered about in serious corridors shows the level of desperation. If the universe is static and eternal, then we are not living in a specific era of life. We are trapped in an infinite, timeless void that has no beginning and no end. This existential dread that time is an illusion and progress is a myth is a heavy psychological toll. However, most evidence still points to expansion, which leaves us with the uncomfortable reality. The Big Bang happened, but it was weirder, faster, and more complex than our simple human narratives can capture. There's a solution to this puzzle that is perhaps the most unsettling of all, the local void hypothesis. This idea suggests that we, Earth and the Milky Way, are living in a relatively empty patch of the universe, a cosmic backwater. Because we are in a low-density region, matter flows away from us toward denser regions faster than average. This would distort our measurements of the universe's expansion rate, creating the illusion of anomalies where there are none. It sounds like a fix, but consider what it means. It means the Copernican principle, the idea that we are not special and that our location in the universe is average, is wrong. We are special, but not in a good way. We are the runts of the litter, living in a desolate, underpopulated void compared to the rest of the rich, dense cosmos. We are isolated in a bubble of emptiness. trying to deduce the laws of the universe from a distorted, lonely perspective. It reinforces the feeling of cosmic isolation, that we are cut off from the real action of the universe, stranded on a desert island in an ocean of stars. This brings us to the Hubble tension, a discrepancy that was annoying before Webb, but is now a full-blown crisis. We measure the expansion rate of the universe, the Hubble constant, in two ways: looking at the early universe, CMB, and looking at the late universe, supernovae. These two numbers should match. They don't. The early universe predicts an expansion rate of 67 kilometers per second /MPC. The local universe measures it at 73 or 74 kilometers per second /MPC. This statistical significance is now 5 sigma, meaning there is a 1 in 3.5 million chance it's a fluke. The universe is expanding faster now than it should be based on how it started. Something is stepping on the gas pedal. Webb's data on early galaxies might be the missing link. If early dark energy existed, a temporary burst of repulsive gravity that existed shortly after the Big Bang, it could explain both the early galaxy formation and the current tension. But introducing early dark energy is like adding a new gear to a clock we thought we understood. It implies the vacuum of space itself is dynamic, shifting, and treacherous. If the vacuum energy of the universe can change, we must confront the concept of vacuum decay. The Higgs field, which gives particles their mass, might not be in its most stable state. It might be in a false vacuum, like a ball resting on a ledge rather than at the bottom of a valley. If the high-energy processes in the early universe, the kind that created these impossible galaxies, hint at a different value for the Higgs field, it suggests the ledge is slippery. A phase transition could occur at any moment. A bubble of true vacuum could nucleate somewhere in the cosmos and expand at the speed of light, rewriting the laws of physics as it spreads. Inside the bubble, chemistry as we know it would be impossible. Atoms would fall apart. It would be an instant, painless, and total deletion of reality. The JWST data, by challenging our understanding of the early high-energy universe, forces us to question the stability of the laws of physics today. Are we standing on solid ground, or on a trapdoor that hasn't opened yet? Let's look at the initial mass function, IMF again. The IMF dictates how many small stars form for every big star. We assume it's universal, that the recipe for baking a galaxy is the same everywhere, but the Webb data suggests the recipe changes. In the early universe, the IMF might have been flat, meaning almost no small stars formed, only giants. This would result in galaxies that are technically dead on arrival, burning through their fuel in a few million years and leaving behind nothing but black holes and neutron stars. These zombie galaxies would shine bright for a moment, and then vanish into darkness forever. If our Milky Way had formed this way, we wouldn't be here. The Sun is a boring small star. We require a bottom-heavy IMF to exist. This implies that the conditions for life are extremely specific and perhaps rare in the history of the universe. We might be the survivors of a cosmic lottery where most galaxies burned themselves out in a gluttonous frenzy at the dawn of time. The sheer number of these anomalies is pushing scientists toward the multiverse hypothesis, not out of wonder but out of necessity. If our universe's laws are so finely tuned and yet so bizarrely contradictory, maybe we are just one bubble in a foaming sea of eternal inflation. In this view, the impossible galaxies are just a roll of the dice in our specific bubble. In another bubble, gravity might be weaker, and no stars ever formed. In another, gravity is stronger, and the universe collapsed back in on itself instantly. We observe this strange, borderline impossible universe because it's the only one complex enough to support observers. This is the anthropic principle weaponized. It tells us, don't ask why the universe is this way. If it weren't, you wouldn't be here to ask. It's a scientific way of saying it's magic, and it leaves many physicists feeling hollow. It feels like giving up on finding a reason and accepting that we are just a statistical accident in an infinite generator of realities. But let's return to the hard data. One specific galaxy, GZ9P3, observed roughly 510 million years after the Big Bang, shows a complex merger shape. Mergers take time. Two galaxies have to drift close, dance around each other, and slowly collide. The process takes hundreds of millions of years. Finding a merger at 510 million years is like finding a car crash in a factory before the cars have even rolled off the assembly line. It implies that these galaxies were born close together, in dense clusters, right from the start. This challenges the idea of a smooth, uniform Big Bang. It suggests the early universe was lumpy and chaotic from t=0. These lumps were the seeds of the monsters we see today. But what caused the lumps? Quantum fluctuations? Or something left over from before the Big Bang? The Penrose conformal cyclic cosmology suggests these lumps are the scars of a previous universe that died. We are looking at the footprints of a dead cosmos stamped onto our own sky. The crisis is not just about galaxies, it's about the chemistry of life. Webb has detected carbon, oxygen, and even neon in these primordial galaxies. These elements are forged in the hearts of dying stars. To see so much of them so early means that generations of stars must have lived and died in the blink of an eye. This is the chemical enrichment problem. It suggests that the universe was seeded with the building blocks of life almost immediately. While this sounds hopeful, in the context of the Fermi paradox, it is terrifying. If the ingredients for life were available 13 billion years ago and countless massive galaxies existed, then where is everyone? If life could have started that early, civilizations should have had billions of years to spread across the cosmos. The fact that we see a silent universe, despite the favorable conditions appearing so early, suggests that something kills life. The Great Filter might be far more effective than we thought. The early universe was rich, fertile, and dead. We are forced to confront the limitations of our simulations. We run computer codes like Illustris or Eagle to model the universe. These simulations use the laws of physics as we know them. They never produce the monsters Webb is seeing. This means our code is missing a line. A force, a particle, or an interaction is missing from our manual of reality. Some propose self-interacting dark matter, that dark matter particles aren't just ghosts, but can bounce off each other, creating friction and speeding up collapse. Others propose that the fundamental constants, like the speed of light, c, or the gravitational constant, g, were different in the past. If g was slightly higher, gravity would be stronger, explaining the rapid growth. But a variable, g, means the universe is not a stable machine. It's a decaying or evolving organism. If the laws of physics can change over time, then we cannot trust that they will remain the same tomorrow. The very bedrock of science, repeatability, is threatened by a universe that changes its own rules. The visual beauty of the James Webb images masks the violence they represent. When you see those red swirls, you are seeing gas moving at thousands of kilometers per second, shock waves rippling through plasma, and gravity crushing matter into oblivion. We call it astronomy, but it is really forensics. We are the detectives arriving at the crime. Consider the sheer scale of the voids between these early galaxies. In the standard model, the universe is a web, with filaments of matter connecting galaxies. Webb is showing us that the knots in the web are huge, but the strands might be thinner than we thought. This cosmic web is the skeleton of the universe. If the skeleton is formed differently, then the muscle, the galaxies, will attach differently. This affects everything down to the local group we live in. It implies that the Milky Way's position and history might be more unique and precarious than we assumed. We are not just a generic galaxy. We might be a rare survivor of a chaotic, hyper-dense epoch that consumed most of its children. The philosophical weight of these discoveries is heavy. For centuries, science has moved us away from specialness. Earth is not the center. The sun is not unique. The galaxy is one of billions. But Webb is hinting at a temporal specialness. We live in a quiet, boring era of the universe, the stelliferous era. Behind us lies a chaotic, monstrous epoch of impossible giants. Ahead of us lies the degenerate era of decaying stars and black holes. We exist in a brief, fragile window of stability. The new data emphasizes just how chaotic the beginning was, making our current tranquility seem like a lucky pause in a violent storm. It makes you wonder when the storm will start again. When will the next phase transition happen? When will the universe decide it is done with this set of rules? There is a term in cosmology called the look-back time. It reminds us that we are never seeing the present. We are always looking at ghosts, When Webb looks at a galaxy at z equals 13, it sees it as it was 13.4 billion years ago. That galaxy likely doesn't exist anymore. It has merged, morphed, or been eaten. We are constructing a history of ghosts. But the problem is, these ghosts look too healthy. They don't look like newborns. They look like veterans. This implies a prehistory that we cannot see. A time before the Dark Ages, where something happened to accelerate evolution. Some fringe theories even suggest the universe didn't start at the Big Bang, but bounced from a previous collapse. If this is a big bounce universe, then the mature galaxies are remnants, survivors carrying the baggage of a previous eon. We might be living in a recycled universe, built on the ruins of the one that came before. The James Webb Space Telescope has only been operating for a short time. We have barely scratched the surface of its capabilities. It is terrifying to think what it will find next. Will we find galaxies at z equals 20, z equals 30? If we find a galaxy that predates the calculated age of the universe, physics will break completely. We will have to admit that age of the universe equals 13.8 billion years is wrong. And if that number is wrong, every calculation based on it, the expansion rate, the density of dark energy, the fate of the cosmos, is wrong too. We are standing on the precipice of a paradigm shift that makes Einstein's relativity look like a minor correction. We are looking for the beginning of time, and we are finding that time might be much deeper than we thought. This is the thrill and the horror of modern science. We build machines to confirm what we know, and they delight in telling us we know nothing. The universe breakers are not just distant lights, they are warning signs. They tell us that the universe is capable of rapid, violent change. They tell us that matter can organize itself in ways we didn't predict. They tell us that the dark is full of monsters. As we continue to analyze the data, we must be prepared to let go of our cherished theories. We must be prepared to accept that reality is stranger, older, and perhaps more hostile than the comforting clockwork universe of Newton and Einstein. The sky is not a static wallpaper. It is a shifting, deep ocean, and we are just realizing how deep the water really goes. Let's consider the imposter theory one last time, but with a twist. What if the redness of these galaxies isn't just redshift or dust? What if it's a signature of population 3 stars? These are the theoretical first stars made of pure hydrogen and helium. They have never been observed. They are the holy grail. If Webb is seeing them, they should be blue-white hot. But if they are surrounded by massive shells of gas, they might appear red. Discovering population 3 stars would be a triumph, but the mass problem remains. Even pure hydrogen stars shouldn't form structures this big, this fast. The puzzle pieces just don't fit. We have the wrong box cover. We are trying to assemble a picture of a garden, but the pieces are forming a dragon. The data is forcing us to look at the dragon. As we move forward in this investigation, we will break down the specific physics of inflation, the split-second expansion that set the stage for the Big Bang. If inflation was bumpy or non-Gaussian, it could explain the early monsters. But non-Gaussian inflation implies a much more complex mechanism driving the early universe, possibly involving multiple quantum fields interacting in a chaotic dance. It turns the smooth, simple beginning into a jagged, unpredictable explosion. This complexity means that calculating the probability of our existence becomes even harder. We are the result of a specific, rare, and chaotic set of initial conditions. We are the survivors of a quantum storm. The story of the early universe is being rewritten in real time. Every week, a new paper comes out challenging the last one. It's dust. No, it's stars. It's black holes. No, it's dark matter. The scientific community is in a state of productive chaos. But for the rest of us, looking up at the night sky, the message is visceral. The stars you see with your naked eye are the local, safe neighborhood. But beyond them, in the deep dark, lies a history of impossible giants and ancient mysteries that defy explanation. We are small, we are late to the party, and we are only just beginning to understand what kind of party it was. We must now turn our attention to the reionization epoch. This is the period when the fog of neutral hydrogen was burned away by the first light. We thought this process took a billion years. Webb suggests it happened in fits and starts, driven by these massive galaxies. They acted like blowtorches, carving bubbles of transparency in the opaque universe. This violent clearing of the fog allowed light to travel freely. But if reionization happened earlier or faster, it changes the thermal history of the intergalactic medium. It means the gas between galaxies was heated to millions of degrees much sooner. This heat affects how future galaxies form. It suppresses the formation of small galaxies. It creates a survival of the fittest scenario, where only the biggest structures can grow. The faint end of the luminosity function is another casualty. We expected to see millions of tiny, faint galaxies for every big one. Webb is seeing a surprising lack of the tiny ones in some fields, and an overabundance of the big ones. Where are the dwarfs? Did they merge, or did they never form? If the small galaxies are missing, then the building blocks of the universe are missing. It supports the top-heavy theory again. The universe started big. This contradicts everything we see around us today, where dwarfs are the most common type of galaxy. Somehow, the universe switched modes from make giants to make dwarves. What triggered that switch? And could it switch back? We are also seeing quenched galaxies, galaxies that have stopped forming stars. As early as 700 million years after the Big Bang, a galaxy is supposed to die after billions of years of burning through its fuel. To find a dead galaxy in the infant universe is like finding a tombstone in a maternity ward. It means these galaxies lived fast, burned all their fuel in a catastrophic burst, and died, all before the universe was even a toddler. What kind of violent event shuts down a galaxy that quickly? An active galactic nucleus? AGN outburst? A shockwave? It paints a picture of the early universe as a place of sudden death, not just slow birth. The geometry of these early galaxies is also puzzling. Many are disk-like. In the chaotic merger model, early galaxies should be messy spheres or trains of clumps. Disks require time to settle down. The rotation has to stabilize. To find calm, rotating disks so early means the chaos settled instantly. It implies a mechanism for order that we don't understand. Is there a stabilizing force we are missing? Or is the viscosity of the early universe gas different? It is another clue that the universe knew what it was doing from the very start, refusing to play by the chaotic rules we wrote for it. Let's not forget the cosmic variance problem. Webb has a small field of view. It's like looking at the sky through a drinking straw. Critics argue we might have just pointed the straw at a lucky spot, a protocluster that is denser than average. But as Webb surveys more fields, CEERS, Cosmos Webb, JADES, the anomalies keep popping up. You can't be lucky everywhere. The consistency of the impossible findings suggests this is not a statistical fluke. This is the texture of reality. The universe is uniformly strange, not just locally strange. The sample size excuse is running out of time. The interaction between dark matter and baryons, normal matter, is described by the halo mass function. If Webb is right, we might need to tweak this function. But tweaking it breaks the predictions for the modern universe. If we change the math to fix the early universe, the modern universe stops making sense. We are caught in a trap. We can explain the past or the present, but not both with the same set of equations. This broken bridge between epochs is the heart of the crisis. We need a unified theory of galaxy formation that works across all time, and right now, we don't have one. We have two separate puzzle halves that don't lock together. Some theorists are turning to primordial non-Gaussianity. This mouthful of a term describes the statistical distribution of the initial density fluctuations. If the universe started with skewed dice, it would produce more extreme peaks, massive galaxies, than a standard bell curve. This would explain the monsters. But proving it requires precise measurements of the cosmic microwave background that we don't have yet. It pushes the answer back to the very first fraction of a second of time. It means the answer lies in the quantum realm, merging cosmology with quantum mechanics, the two theories that notoriously hate each other. We must also consider the sound horizon. In the early plasma, sound waves traveled through the fluid, creating ripples. These ripples determined where matter would clump. This scale, the baryon acoustic oscillations, BAO, is a standard ruler for the universe. If the early galaxies are messing with our understanding of expansion, they might be messing with the length of this ruler. If our ruler is the wrong length, then our distance measurements to everything, Stars, galaxies, the edge of the visible universe are wrong. The scale of the cosmos itself is in question. Are we in a smaller, younger universe, or a larger, older one? The technological marvel of Webb is that it sees heat. Infrared is heat radiation. We are seeing the thermal signature of the ancient past. But heat can be tricky. Is the heat from stars? Or from friction? Or from dark matter annihilation? The spectral energy distribution, SED fitting, is an art form. We fit models to the data points. But if our models of early stars are wrong, e.g., if population 3 stars act differently, then our fits are wrong. We might be misinterpreting the signal entirely. We are reading a language we don't fully speak, translating brightness into mass, using a dictionary written for the modern universe, not the ancient one. The clumpiness of the universe is measured by a parameter called SIGMA8. There is a tension here too. The early universe, CMB, predicts a certain clumpiness. The modern universe, lensing, measures a lower one. The Webb galaxies suggest a higher clumpiness. We have 3 different values for the same parameter. This sigma-8 tension is another crack in the dam. It suggests that structure growth is not linear. It speeds up and slows down. What controls the throttle? Dark energy? Or something else? A fifth force? The more we look, the more variables we have to add to the equation to make it balance. Let's talk about dust production. Dust is made by dying stars. It takes time, a lot of time. To see dusty galaxies at z=10 is baffling. Where did the dust come from so quickly? It requires supernova to go off almost immediately after stars form. It implies a universe that was recycling itself furiously from the very first moment. This dust is crucial because it shields life. Without dust, you can't form rocky planets. You can't form Earths. The presence of early dust suggests that the potential for rocky planets and life existed much earlier than we thought. We might be the latecomers to a galaxy that has been habitable for 13 billion years. The existential horror comes from the realization of our own ignorance. We built the standard model over decades, we gave Nobel Prizes for it, we taught it to students. And nature just swatted it aside with a few photons. It is a humbling reminder that the universe is not obligated to make sense to us. It is not obligated to follow the beautiful or simple equations we like. It can be messy, chaotic, and confusing. The map is not the territory. And right now, we are realizing we don't even have a map. We are lost in the woods, and the trees are much bigger than they should be. As we approach the end of this investigation into the early universe, we must face the simulation hypothesis again. If the universe is a simulation, maybe the early universe is just a low-resolution background texture. Maybe the anomalies are rendering errors. When we look too closely at the start of the simulation, we see the pixels. We see the procedural generation algorithms struggling to create consistent data. The impossible galaxies are glitches in the code. It's a sci-fi concept, but when the physics stops working, the line between science and philosophy blurs. We are probing the limits of the system, and the system is glitching. Or perhaps the truth is more organic. The universe is evolving. The laws of physics are the DNA of the cosmos, and they mutate. The early universe had different DNA. It allowed for rapid growth. Then, a phase transition occurred, a genetic mutation that slowed things down, stabilized gravity, and allowed for long-lived stars like the Sun. We live in the stable phenotype of the universe. But if it mutated once, it can mutate again. We are not in a static crystal. We are in a growing, changing beast. And we are just cells in its body, unaware of the larger shifts in its physiology. The James Webb Telescope is a time machine. But unlike fiction, this time machine doesn't let us change the past. It only lets us witness the crime of impossible creation. We are witnesses to a miracle that shouldn't have happened. The formation of these galaxies is a miracle of probability. If we accept the standard model, the odds of these galaxies existing are 0. Therefore, the standard model is dead. Long live the new physics, whatever that turns out to be. We are in the interregnum, the chaotic time between kings. where old laws are gone and new ones haven't been written yet. What if dark energy wasn't constant? What if it was strong early on, pushing things apart, then weak, then strong again? This dynamic dark energy could fix the Hubble tension and the early galaxy problem. But it makes the universe a roller coaster. It means the expansion doesn't just accelerate, it wobbles. A wobbling universe is unstable. It could rip itself apart or crush itself on a whim. We are riding a bucking bronco, not a smooth train. The ride is wilder than we admitted. The cosmic dawn was supposed to be a sunrise. Slow, gentle, Webb shows us a cosmic explosion, a flashbang of creation. This changes the narrative of our origins. We are not the children of a slow dawn. We are the children of a sudden, violent burst. It makes our existence feel more precarious. If creation is explosive, destruction might be too. We look for symmetry in nature. The beginning mirrors the end. A violent birth suggests a violent death. We are now looking for population 3 supernovae. If we find them, they will tell us what the first stars were made of. If they are absent, it deepens the mystery. The absence of evidence is becoming evidence of something strange. Maybe the first stars didn't explode. Maybe they imploded directly to black holes. A silent generation of stars that left no trace but gravity. We are hunting for ghosts that refuse to leave footprints. The final piece of this investigative puzzle is the Great Attractor. While not directly an early universe object, the anomalies in the early universe affect our understanding of large-scale flows today. If the early universe was lumpier, then the Great Attractor pulling our galaxy might be a remnant of those primordial monsters. We are still feeling the gravitational tug of the universe breakers across 13 billion years. The past is pulling on the present. We are being dragged by the ghosts of the beginning. So where does this leave us? We have a telescope that works perfectly, data that is robust, and a theory that is crumbling. We are standing in the rubble of the Lambda CDM model, holding the pieces of impossible galaxies in our hands. The investigation is far from over. In fact, the mystery has just deepened. We have ruled out the easy answers. Now we must face the hard ones, the ones that require us to rewrite the laws of reality. The universe is not what we thought it was. It is bigger, older, stranger, and scarier. And we are just beginning to open our eyes. If the universe built massive galaxies this quickly, it forces us to ask the most terrifying question of all. Where is everyone? This is the Fermi paradox amplified to a deafening scream. Previously, we thought life took billions of years to evolve because the universe needed time to settle down. We believed that first, you needed a generation of stars to live and die to create the heavy elements, carbon, oxygen, iron, required for rocky planets and biological cells. We call this metallicity. The assumption was that the early universe was too metal-poor to support life. But the James Webb Telescope has detected chemically enriched atmospheres and massive, stable galaxies, just 500 million years after the Big Bang. This means the ingredients for life were present 13 billion years ago. If life could have started then, it has had a 13 billion year head start on us. A civilization with that much time would be indistinguishable from gods, capable of engineering galaxies. The fact that we see no Dyson spheres, no megastructures, and hear no radio signals implies that despite the fertile conditions, something kills civilizations before they can conquer the stars. The Great Filter is real, and it is incredibly efficient. Consider the environment of these early universe breakers. While they had the chemical ingredients for life, they might have been bathed in lethal radiation. The star formation rates Webb is seeing are extreme, thousands of times faster than in the Milky Way. This means supernovae were going off constantly, like popcorn in a microwave. A nearby supernova can strip a planet of its atmosphere and sterilize its surface in seconds. If the early universe was a crowded, violent factory of giant stars, then perhaps life started billions of times, only to be burned away billions of times. We might be the first civilization to arise in a quiet epoch, where the universe has finally become boring enough to allow life to survive for more than a few million years. This theory, the gamma-ray burst sterilization hypothesis, suggests that for the first 10 billion years the cosmos was a kill zone, and we are merely the moss growing on the ruins now that the fires have died down. But what if the silence isn't because everyone is dead? What if it's because the physics of the early universe allowed for a different kind of life? Dark life. We assume life needs carbon and water. But in a universe dominated by dark matter halos and potentially dark stars, perhaps life evolved in the dark sector. Webb cannot see dark matter directly, but it sees the gravitational skeletons it builds. If complex structures formed in the dark sector 13 billion years ago, there could be a shadow biosphere coexisting with us, completely invisible to our sensors. We look for radio waves and heat signatures, but a civilization built of dark matter would interact only via gravity. They could be passing right through us, unaware or indifferent to our baryonic existence. The crowded nature of the early universe suggests that the dark side of the cosmos might be the populated side, and we are the ghosts made of rare, glowing dust. Let's return to the Hubble tension, because it is the gun pointing at the head of cosmology. The discrepancy between the expansion rate measured by Webb using early universe data and the rate measured by local supernovae is not going away, it is getting worse. The local universe is expanding faster than it should be. This implies that dark energy, the mysterious force pushing the universe apart, is getting stronger over time. This is a nightmare scenario known as phantom dark energy. If dark energy grows, it won't just push galaxies away from each other. Eventually, it will overcome the gravity holding galaxies together. Then it will overcome the gravity holding solar systems together. Then planets. And finally, atoms. This is the big rip. The Webb data, by confirming the high-density early universe, creates a stark contrast with the rapid local expansion, suggesting that the rip might happen sooner than we calculated. We are on an accelerating treadmill that ends in the disintegration of matter itself. The data also challenges our concept of time in the early universe. According to Einstein, time is relative to gravity. In regions of intense gravity, time moves slower. The early universe was denser, with matter packed tighter together. Webb is looking at a time when the universe was effectively a massive gravity well. This leads to the time dilation problem. Are we measuring the age of these galaxies correctly? If they existed in a region of extreme gravitational warping, a billion years for them might be only a few million years for us. This could explain how they evolved so fast. They effectively had more time than our clocks suggest. But if time flowed differently back then, our entire timeline of the Big Bang is a distortion. We are trying to map history with a ruler that changes length every time we move it. It suggests that 13.8 billion years is a meaningless number, a human approximation of a fluid, shifting temporal reality. There is a chilling theory called the false vacuum, which connects to the stability of the universe. We assume the vacuum of space is empty and at its lowest energy state. But quantum mechanics allows for metastable states. The violence of the early universe observed by Webb, the rapid formation, the intense radiation, suggests high-energy processes that we can't replicate. If these processes pushed the vacuum of space to the brink, it implies that the fabric of reality is stressed. Imagine a frozen lake. We are skating on it. Webb has looked down through the ice and seen that it is much thinner than we thought, and the water below is boiling. If the vacuum decays, a bubble of new physics expands at the speed of light, rewriting the laws of chemistry. We wouldn't see it coming, we would just cease to exist. The fact that the universe was so energetic so early hints that we might be living on borrowed time, waiting for the ice to crack. We must also confront the horizon problem anew. The cosmic microwave background is incredibly uniform, the same temperature in every direction. Standard theory says this is because of inflation, a period of faster-than-light expansion that smoothed everything out. But Webb's galaxies are clumpy. They show structure, density, and variance that fights against the smooth background. This creates a paradox. How can the background be smooth while the foreground is lumpy? It suggests that inflation might not have happened the way we think. Maybe the universe didn't expand from a single point. Maybe it was a collision of brains, two higher-dimensional realities crashing together. In brain cosmology, the Big Bang is just the moment of impact. If this is true, the impossible galaxies are the debris from the collision, formed instantly by the shockwave of two universes hitting each other. We are living in the wreckage of a multi-dimensional car crash. Let's look at the black hole seeds again. The existence of supermassive black holes at z equals 11 is the single hardest thing to explain. A black hole of 10 million solar masses cannot form from a star. It requires a massive cloud to collapse directly. But gas clouds usually fragment into stars as they collapse. To get a direct collapse black hole, you need to stop the gas from cooling. You need a source of intense UV radiation to keep the gas hot so it doesn't fragment. This requires a nearby massive, radiation-pumping galaxy. This creates a chicken and egg problem. You need a galaxy to make the radiation to make the black hole, but the black hole is supposed to be the seed for the galaxy. Webb is showing us both existing simultaneously. It suggests a symbiotic, parasitic relationship at the dawn of time, where black holes and galaxies formed in a chaotic embrace, feeding off each other in a runaway process that physics struggles to model. The visual isolation of these early galaxies is also deceptive. Webb shows them as islands in the dark, but the space between them, the intergalactic medium, IGM, was not empty. It was filled with neutral hydrogen. This gas is the fuel for future stars. The way these galaxies polluted the IGM with heavy elements is crucial. Webb has detected oxygen in the gas between galaxies. This means the early galaxies were blowing their guts out, ejecting massive amounts of material into the void. This galactic wind was so powerful it traveled hundreds of thousands of light years. It paints a picture of the early cosmos as a violent storm of matter, where galaxies were not closed systems but open wounds, bleeding heavy elements into the dark. This enriched gas eventually fell back to form us. The iron in your blood was likely forged in one of these violent, impossible outbursts 13 billion years ago, blown out of a dying hypergalaxy. The cosmic variance excuse that we just looked at a weird spot is dying. The JADES, JWST Advanced Deep Extragalactic Survey Deep Field confirmed the findings of CEERS. The universe is consistently breaking the rules. This uniformity of anomalies suggests that the rules themselves are the problem. We are using the general relativity rulebook, but at the scales of the very large, early universe expansion, and the very small, singularity formation, general relativity breaks down. We have known this for decades, but we ignored it because we didn't have data that forced us to look at the cracks. Webb is the light shining through the cracks. We need a theory of quantum gravity to explain these galaxies. We need to marry Einstein with quantum mechanics. Until we do, we are describing the universe with a broken language. We are trying to describe a color we have never seen using only black and white. There is a distinct possibility that the redshift we observe is not entirely due to expansion. This is the gravitational redshift component. If these early galaxies are incredibly dense, the light struggling to escape their gravity well would lose energy and turn red. This would make them look further away and older than they actually are. If we are misinterpreting gravitational redshift as cosmological redshift, then these galaxies might be closer and younger. This would solve the impossible mass problem but create a density problem. It would mean objects in the early universe were compacted to densities we can't imagine, verging on becoming giant black holes. It implies that matter was crushed into states of existence that we have no laboratory to test. We might be looking at quark stars or boson stars, exotic states of matter that only exist under the crushing weight of a primordial universe. Let's talk about the Great Void. Recent studies suggest that our Milky Way resides in a KBC void, a region of space roughly 2 billion light-years across that is significantly underdense compared to the rest of the universe. This matters because if we live in a bubble of emptiness, our local measurements of the Hubble constant are distorted by the outflow of matter towards the denser regions. Webb's view of the distant, dense universe contrasts sharply with our local, empty neighborhood. It suggests we are cosmic hillbillies living in the sticks, far away from the bustling metropolitan centers of the universe. This isolation might be why we are here. The dense regions might be too dangerous, too radioactive, too chaotic for life. We survive only because we are in the boring, empty, lonely part of the cosmos. Our loneliness is our shield. One of the most haunting discoveries is the shape of these early galaxies. We call them pickles, or bananas, because they are elongated, prolate spheroids. They are not the beautiful spirals or fuzzy blobs we expected. They are cigars of stars. This shape suggests that they formed along the filaments of the cosmic web, like beads on a string. It implies that the cosmic web, the invisible scaffolding of dark matter, was the dominant force, shaping galaxies into tubes rather than disks. This filamentary mode of growth is much more efficient than the merger mode we used to believe in. It means the universe has a highway system, and matter flows along these dark roads at incredible speeds. We are just a rest stop on one of these dark highways, and the traffic is moving faster than we thought. The UV turnover is another technical detail with scary implications. Galaxies emit ultraviolet light. As this light travels, it gets absorbed by hydrogen, but Webb sees a lot of UV light coming from these distant sources. This means the universe was, quote, transparent to UV light much earlier than expected. For the universe to be transparent, the hydrogen fog had to be ionized. This requires a staggering amount of energy. The photon budget needed to clear the fog is huge. The only way to get that budget is if the number of stars or black holes was vastly higher than predicted. It implies the early universe was blindingly bright. If you could stand on a planet back then, the night sky wouldn't be black. It would be a glowing wall of ultraviolet fire. It was a universe of light, but a light that would burn you to ash. Let's revisit the simulation theory through the lens of computational efficiency. In a video game, the distant mountains are low resolution. They only gain detail when you get close. We just built a telescope that effectively zoomed in on the distant mountains of the universe, the early galaxies. And we found that they have too much detail. They are not low-res background textures. They are fully rendered high-fidelity objects. To a simulation theorist, this is baffling. Why waste processing power rendering the Big Bang in such high detail if no one was there to see it? Unless the simulation isn't running for us. Maybe we are not the players. Maybe the players are the ones who were around 13 billion years ago, and we are just the decaying code left running on a forgotten server. The universe breakers were the main characters, and we are the NPCs in the sequel that no one is playing. The concept of cosmic Darwinism might explain the anomalies. Proposed by Lee Smolin, it suggests that black holes give birth to baby universes. Universes that produce more black holes have more children. Therefore, the laws of physics evolve to maximize black hole production. The Webb data fits this perfectly. We see massive black holes forming instantly. We see galaxies designed to feed black holes. It looks like our universe was bred for one purpose: to make singularities. We are living in a reproductive machine. Stars, planets, and life are just byproducts of the black hole manufacturing process. We are the sawdust in a factory making gravitational crushers. It creates a sense of cosmic insignificance that is hard to shake. We are not the purpose, we are the waste. The James Webb Telescope operates at L2, a Lagrange point 1.5 million kilometers from Earth. It is cold, lonely, and far from help. If it breaks, we cannot fix it. It is a fragility that mirrors our own. We are clinging to a rock in a universe that seems increasingly hostile to our understanding. The crisis in cosmology is not just about math. It's about the psychological safety of knowing our place. We used to think we knew the story, Big Bang to cooling to stars to us. A straight line. Now the line is a squiggle, a loop, or maybe a fracture. The story has changed, and we don't know the ending anymore. We don't even know if we are in the middle or the end. What if the Big Bang was actually a big splat? The ekpyrotic universe theory suggests our universe is the result of two brains colliding in a higher dimension. This cycle happens eternally. Bang, expansion, contraction, bang. If this is true, the mature galaxies Webb sees might be echoes of the structure that existed in the universe before this one. Imagine writing on a chalkboard, erasing it, and writing again. Sometimes, the faint chalk marks of the previous lesson are still visible. The universe breakers might be the chalk marks of the previous eon, ghost structures that survived the reset. It means nothing is truly new. We are just repeating a cycle of creation and destruction that has happened infinite times and will happen infinite times again. It makes our struggles, our history, and our future feel incredibly small, just one tick in an eternal clock. The mass-to-light ratio is a key tool we use to weigh galaxies. We count the light and estimate the mass, but Webb finds galaxies that are surprisingly bright for their estimated mass, or surprisingly massive for their size. This disconnect implies that light is not a reliable narrator. In the early universe, there might have been sources of luminosity we don't understand, mini quasars. accretion disks around neutron stars, or dark matter annihilation. If we can't trust the light, we are blind. We are interpreting shadows on a wall, assuming they are rabbits when they might be wolves. The universe is hiding its true nature behind a mask of misleading photons. We're also seeing globular clusters forming in the early universe. These are tight balls of millions of stars. In the Milky Way, they are ancient fossils. Webb sees them as newborns. But even as newborns, they are incredibly dense. To pack 1,000,000 stars into a space just a few light-years across requires conditions of extreme pressure. It's like packing the entire population of Earth into a single elevator. The night sky inside a globular cluster would be blindingly white, with no darkness ever. If civilizations evolved inside these clusters, they would never see the outside universe. They would never know about the Big Bang or the expansion. They would think the universe was a static, eternal box of light. It makes you wonder, what are we not seeing because of our local environment? What box are we trapped in? The end of the Dark Ages was supposed to be a gradual dawn. But Webb suggests it was a phase change, like water freezing into ice. Sudden, global, irreversible. This reionization event transformed the universe from opaque to transparent. The energy required to do this is staggering. It implies that the first generation of objects, whether stars or black holes, were incredibly energetic. They effectively burned the universe clear. We are living in the clear, burned-out aftermath. The fog of the beginning is gone, but so is the mystery. We are left with the transparent, cold void. The exciting part of cosmic history, the burning, is over. We are the ash settling after the fire. Let's consider the arrow of time. Thermodynamics says entropy, disorder, must always increase. The early universe was low entropy, highly ordered. The Webb galaxies, being so structured, suggest that entropy increased faster than we thought. The universe disordered itself into galaxies at a breakneck speed. This means the heat death, the final state of maximum entropy where no energy flows and everything is dead, might come sooner. We are burning through the universe's battery faster than predicted. The lights will go out earlier. The big freeze is rushing towards us, accelerated by the voracious appetite of the early cosmos. The discovery of complex organic molecules in galaxies 12 billion light-years away is a biological smoking gun. Polycyclic aromatic hydrocarbons, PAHs. These are the building blocks of life. They are everywhere. It means the universe is not dead rock. It is a prebiotic soup. The entire cosmos is marinating in the potential for life. This makes the silence even more terrifying. It's like walking into a fully stocked kitchen with food cooking on the stove, but the house is empty. The table is set, the ingredients are fresh, but the guests are missing, or they are hiding in the pantry, afraid of whatever is outside. The axis of evil is a controversial anomaly in the cosmic microwave background. It's a line that seems to align with the plane of our solar system. For years, it was dismissed as a data glitch. But Webb's discovery of early galaxies aligning along filaments gives new life to the idea of large-scale alignments. If the entire universe has an orientation, a preferred direction, it violates the cosmological principle of isotropy, sameness in all directions. It implies the universe has a structure, a top and a bottom, a north and a south, and we are aligned with it. This hints at a rotating universe, or a universe with a specific geometry, like a donut, torus, rather than an infinite flat plane. If the universe is rotating, it has a center, and centers are dangerous places. We must ask, is the speed of light actually constant? Some theories like variable speed of light, VSL, suggest that c was much faster in the early universe. This would solve the horizon problem without inflation. It would explain how early galaxies formed so fast. Information traveled faster. But if light slows down over time, it means we are slowly being blinded. The event horizon of the universe is shrinking. We are becoming more and more isolated as the speed of causality slows. Eventually, light might stop entirely, freezing the universe in a time halt. The Webb data fits a VSL model disturbingly well, suggesting the speed limit of the cosmos is essentially a brake pedal that is being pressed down. The cosmic dawn might actually be a cosmic dusk for a previous cycle. This is the cyclic universe theory again. Webb is looking at the ashes of the previous big crunch that bounced into our Big Bang. The impossible galaxies are the clotted remains of the previous universe's black holes. We are built on a graveyard. Every atom in your body has been used before in a previous iteration of reality. We are recycled ghosts. This endless cycle of birth, death, and rebirth renders any single civilization meaningless. We are just Sisyphus, rolling the rock of existence up the hill, only to watch it roll down and explode into a Big Bang again, forever. The lithium problem is an old mystery that Webb is reviving. The Big Bang theory predicts how much lithium should exist. We observe only a third of that amount. Where did the lithium go? Did the early monsters eat it? Did it decay into something else via unknown physics? The missing lithium is a hole in our accounting books. It suggests we don't understand the nuclear furnace of the Big Bang. If we can't calculate the amount of lithium, how can we calculate the stability of the vacuum? It's a loose thread that, if pulled, might unravel the entire sweater of modern physics. The clumping problem extends to dark matter. We assume dark matter is cold, slow-moving. But if it were fuzzy or warm, it would change how galaxies form. Webb's data on the smallest galaxies, or lack thereof, might support fuzzy dark matter. This matter acts like a wave, not a particle. It interferes with itself. It implies the foundation of the universe is not solid matter, but a quantum wave function spread across billions of light-years. We are floating on a quantum ocean. The solidity of the world is an illusion created by the interference patterns of this dark ocean. And waves can crash. Let's focus on the black hole merger rates. If early black holes were common, they must have merged frequently. These mergers release gravitational waves. We are building detectors like LISA to hear them. Webb is the scout telling Lisa where to listen. But if the background hum of gravitational waves is too loud, a stochastic background of millions of merging black holes, it might drown out everything else. Space-time itself might be vibrating constantly from the echoes of these ancient collisions. We are living in a noisy room, but our ears, gravitational detectors, are not sensitive enough to hear the screaming yet. When we turn them on, we might go deaf from the noise of the violent past. The cosmic dipole is a measurement of our speed through the universe. We are moving towards the constellation Leo at 370 kilometers per second. But recent measurements suggest this speed is inconsistent with the expansion. We are being pulled by something massive beyond the observable horizon. The dark flow. Webb's confirmation of massive early structures hints that the universe is not uniform beyond our horizon. There might be superstructures, titanic walls of matter billions of light-years long, tugging on us. We are drifting in a current caused by monsters we can never see because they are outside our light cone. We are being pulled into the dark by an invisible hand. The crisis forces us to reconsider the anthropic principle. If the early universe was so different, so hostile, and yet we are here, it suggests that life is incredibly resilient, or incredibly lucky, or it suggests that we are not the first. The Grabber hypothesis suggests ancient civilizations from the early epochs could have expanded and grabbed resources, leaving us in a depletion zone. Maybe the void we live in is a mining quarry that was exhausted billions of years ago. We are living in the strip-mined leftovers of the universe. The impossible galaxies were the cities of the miners. They are gone now, or they moved on to better universes. There is a specific galaxy, CEERS 93316, that was a candidate for Z equals 1,6. Later, it was revised to Z equals 4.9. This revisionism is happening, but it doesn't solve the problem. Even at Z equals 4.9, it is too bright and too massive. The calibration excuse only goes so far. The objects are still weird. It's like mistaking a giant for a mountain. You realize it's not a mountain, but it's still a giant. The scale of the anomaly shifts, but the anomaly remains. The universe is stubbornly refusing to fit into our boxes. It is wild, overgrown, and untamed. The metallicity floor is the minimum amount of metal needed to form a planet. We thought it took billions of years to reach this floor. Webb shows we hit the floor almost instantly. This means Earth-like planets could have formed 13 billion years ago. Imagine an Earth formed at the dawn of time. It would have seen a sky filled with quasars and forming galaxies. It would be an ancient, senile world now, orbiting a dying white dwarf. The ruins of such worlds must be out there, trillions of fossilized planets, drifting in the dark, holding the secrets of the first life. We are searching for them, but the graveyard is vast. The James Webb is not just a telescope, it is a philosophical wrecking ball. It has destroyed the gradualism narrative. The universe is not gradual. It is punctuated equilibrium. Long periods of boredom interrupted by moments of sheer terror. The Big Bang, reionization, the dark energy takeover. These are violent shifts. We are currently in a boring period. But the data suggests the universe is prone to snapping. What is the next snap? Vacuum decay? The Big Rip? Or something we haven't named yet? The impossible galaxies are the evidence that the universe snaps hard. Let's end this section with the observer effect. Quantum mechanics says the observer affects the reality. By looking at the early universe, are we collapsing its wave function? Are we forcing it to choose a history? It sounds like mysticism, but in the quantum universe, history is not fixed until it is measured. Wheeler's delayed choice quantum eraser experiment proves this. By building Webb and looking back, we might be retroactive creators of the early universe. We are defining the past by observing it. The monsters exist because we looked for them. We are caught in a loop of our own perception, creating the mystery we are trying to solve. The sheer density of information Webb transmits is overwhelming, 50 gigabytes of data a day. It is a fire hose of reality. Buried in that data are likely signals we are missing. Technosignatures, pollution in the atmosphere of an exoplanet, laser flashes, Dyson sphere transits. The universe breakers are the loud noise, but the signal of life might be a whisper underneath. We are so focused on the giant galaxies that we might be missing the small, artificial lights. The aliens could be waving at us, but we are too busy looking at the explosions in the background. The cosmic variance argument implies that different parts of the universe have different histories. This breaks the cosmological principle. It means the universe is not the same everywhere. If physics varies from place to place, then universal laws are actually local bylaws. In a distant galaxy, gravity might be repulsive. In another, electromagnetism might be stronger. We can only survive in our local bylaw zone. If we traveled to the impossible galaxies, we might dissolve because the rules of chemistry there are incompatible with our biology. We are trapped in our local bubble of physics. The population 3 stars, if they exist, are the ancestors of everything. They are the Adam and Eve of the cosmos. But they were monsters. 300 times the mass of the Sun. Blue giants. They lived for only 2 million years. They died in pair instability supernovae. Explosions so powerful they ripped the star apart completely, leaving no black hole, just pure enriched gas. This total sacrifice seeded the universe with life. We are here because the first generation of stars committed suicide completely. It is a poetic, violent origin story. We are the children of dead giants. The cold spot in the CMB is another anomaly, a vast region that is too cold. Some say it is the imprint of a parallel universe bumping against ours. If Webb finds that the impossible galaxies are clustered near the cold spot, it would link the two mysteries. It would suggest that the bump from the multiverse not only cooled that region, but injected extra matter, seeding the massive galaxies. We would have physical evidence of a multiverse collision. The bruise on the sky would be a portal to another reality. We are approaching the limits of what baryonic physics can explain. The anomalies point to new physics. This is not just adding a particle, it's changing the framework. String theory, loop quantum gravity, holographic principle. These theories have been starving for data. Webb is feeding them. The holographic principle suggests the 3D universe is a projection from a 2D surface. If the projection has artifacts or glitches, the anomalies, it supports the idea that we are a hologram. The universe breakers are the pixelation errors in the projection. The Dark Ages were not dark. They were invisible to our eyes, but likely blinding in other spectrums. Webb sees the infrared. But what about the X-ray? The neutrino background? If we could see in neutrinos, the early universe might look like a blazing inferno. We are sensing only a tiny slice of reality. The mystery is partly a result of our blindness. We are blind men touching an elephant, screaming that it feels like a snake, the galaxies. We need to open our other eyes, gravitational waves, neutrinos, to see the whole beast. The redshift 13 inches barrier is psychological. Once we break it confirmedly, the floodgates open. We will find z equals 1,5, z equals 2,0. We are racing back to the singularity. But z equals infinity is the Big Bang. We can never see it with light because the universe was opaque. We are approaching the opaque wall. Webb is taking us to the wall and pressing our faces against it. We can hear the banging on the other side, gravitational waves, but we can't see through. The wall hides the moment of creation. And maybe it's good that it does. Seeing the naked singularity might be too much for the human mind. The cosmic web is evolving. Webb shows the filaments were thicker and shorter in the past. The web is stretching. As it stretches, the connections break. Eventually, galaxies will be isolated. The connected universe is a temporary phase. We are moving into the disconnected era. The Internet of Galaxies is going offline. We are losing contact with the rest of creation. The silence will only grow deeper. We are the last generation to see a connected cosmos. The stellar feedback loops are broken. In simulations, exploding stars push gas out, stopping star formation. In the early universe, this feedback failed. The gas kept falling in. Why? Was gravity stronger? Or was the gas stickier? Maybe magnetic fields played a role. Primordial magnetism. If the early universe was highly magnetized, it would channel gas like a railgun into the centers of galaxies. A magnetic universe is a terrifying concept. Giant magnetic storms spanning light years, crushing stars. The Lyman alpha forest is a pattern of absorption lines in quasar spectra. It maps the hydrogen gas. Webb is finding that the forest is clearer than expected near these galaxies. They are clear-cutting the forest with their radiation. This aggressive environment implies that early galaxies were toxic to their surroundings. They were not life-givers. They were radiation cannons clearing a path through the dark. To survive near one would be impossible. We need the gentle, slow galaxies of today. The ancient giants were destroyers. Cosmic noon is the peak of star formation 3 billion years after the Big Bang. Webb is finding a cosmic dawn that rivals cosmic noon. 2 peaks? This implies a booming and busting economy of stars. The universe had a manic episode at the start, crashed, and then boomed again. This cyclical volatility makes the universe feel organic, like a heart beating. Pulse 1. Dawn. Pulse 2. Noon. Pulse 3. Is coming? Or are we in the flat line? The impossible galaxies might be sphalerons, rare quantum events that violate baryon number conservation. If the early universe was hot enough, matter could be created from nothing via sphalerons. This would explain the mass. It's not matter gathering, it's matter appearing. Spontaneous generation. If matter can pop into existence, then the conservation of energy is a local law, not a universal one. The universe is a free lunch, and it's eating itself. We are small. The universe is big. This is the cliché. But Webb makes us feel temporally small. We occupy a nanosecond of cosmic time. The real history happened before we arrived. The giant wars of gravity and radiation were fought and won in the first billion years. We are touring the battlefield long after the treaty was signed. We see the craters, black holes, and the ruins, ancient galaxies, but we missed the war. We are tourists in a museum of violence. The cosmic horizon is the limit of our knowledge. Webb pushes it back, but it also highlights how much is hidden. 95% of the universe is dark energy and dark matter. We see 5%, and of that 5% we only understood the modern mode. The ancient mode of the 5% is now confusing us. We understand less than 1% of reality. We are confident idiots, strutting around with a standard model that fails the moment we test it. Humility is the only scientific stance left. As we move to the final phase of our analysis, we must look at the future of the past. How will these discoveries change our future? If we accept the universe breakers, we must accept that gravity is a variable monster. This means our solar system is not safe. It means the stability of the sun is not guaranteed. It means the universe is a wild animal that we have mistaken for a pet. And the animal is waking up. The cage of standard physics is breaking. We are about to find out what lives outside the cage. The term crisis in cosmology is thrown around in headlines, but few understand the violence implied by that word. In science, a crisis means the map has stopped matching the territory. We are currently navigating the universe using a map drawn in the 1980s, and the James Webb Telescope has just revealed that the coastline is miles away from where it should be. The Hubble tension is the centerpiece of this crisis. It is a discrepancy between how fast the universe is expanding today versus how fast it was expanding in the beginning. We expected these two numbers to agree, connected by a smooth curve of cosmic evolution. They do not agree. The universe is accelerating faster than our physics can explain. This implies there is an extra energy source, a ghost in the machine, pushing on the accelerator. Webb's confirmation of early massive galaxies adds fuel to this fire because it suggests the universe was revving high right from the start. We are trapped in a vehicle that is speeding up uncontrollably, and we have no idea who or what is driving. Let us delve into the Methuselah star problem which Webb has reignited. We have observed stars like HD 140283 that appear to be older than the universe itself. The calculated age of the universe is 13.8 billion years. Some stars appear to be 14.5 billion years old. You cannot be older than your mother. Previously, we dismissed this as measurement error. But Webb's deep field data suggests that the epoch of formation was much earlier than we thought. If the universe created stars instantly at t equals 0, or if the universe is actually older than 13.8 billion years, the math balances. But making the universe older breaks the expansion rate calculations. It is a zero-sum game. If you fix the age, you break the expansion. If you fix the expansion, you break the age. We are trying to fit a square peg into a round hole, and the peg is the size of a galaxy. The universe is refusing to be consistent, which is a terrifying trait for a reality we rely on to be stable. The concept of early dark energy is gaining traction as a desperate fix. Imagine that, shortly after the Big Bang, a surge of anti-gravity energy appeared, expanded the universe violently, and then vanished. This phantom pulse would explain why the early universe looks so mature. It was inflated rapidly. But proposing a force that turns on and off at will is scientifically uncomfortable. It sounds like a god of the gaps. If dark energy can switch on and off, what stops it from switching on right now? A sudden surge of early dark energy today would tear the solar system apart in minutes. We are assuming the engine of the cosmos is constant, but the data hints that it might be glitchy, prone to surges that rewrite the landscape of existence. We might be living in a lull between pulses. There is a chilling implication regarding the fine structure constant alpha. This constant determines the strength of the electromagnetic force, how strongly atoms hold onto their electrons. If alpha were slightly different, matter wouldn't hold together. Webb's observations of quasar absorption lines in the deep past suggest that alpha might not be constant. It might vary across space and time. If the laws of physics are fluid, then there are regions of the universe where you would simply dissolve. We exist in a quote-quote zone of physics. The impossible galaxies might have formed in a region where physics was turbocharged, allowing for rapid growth. But this means universal laws are a myth. We are navigating a chaotic sea where the water can turn to acid without warning. It fundamentally destabilizes the concept of a unified reality. The great filter is usually applied to biology, but we should apply it to cosmology. Maybe universes that expand too fast tear themselves apart before life can form. Maybe universes that expand too slow collapse into black holes. We are in the Goldilocks universe. But Webb suggests our universe was dangerously close to the too fast edge in the beginning. We skirted the edge of destruction. The sheer number of massive black holes early on suggests a near-death experience for the young cosmos. It nearly cannibalized itself. We are the survivors of a cosmic infant mortality crisis. The universe tried to kill itself with gravity at the start, and now it is trying to kill itself with expansion at the end. Life is just a brief mold growing on the corpse between the murder and the suicide. Let's consider the information paradox. Stephen Hawking famously realized that black holes destroy information, which violates quantum mechanics. If the early universe was filled with supermassive black holes, as Webb suggests, then massive amounts of information about the early cosmos were deleted. Eaten. Gone forever. This means we can never fully reconstruct the past. The history book has pages torn out. We are trying to understand the story of creation, but the main chapters were shredded by the universe breakers. We are suffering from cosmic amnesia. We will never know what came before the black holes because they erased the evidence. We are detectives at a crime scene where the bodies were dissolved in acid. The cosmological constant problem is often called the worst prediction in the history of physics. Quantum field theory predicts a value for vacuum energy that is 120 orders of magnitude higher than what we observe. Webb's data, by forcing us to reevaluate the energy density of the early universe, is poking this sleeping bear. If the vacuum energy was different in the past, it implies the constant is a variable. If it shifts even a tiny fraction towards the theoretical prediction, the universe explodes instantly. The fact that we exist implies a cancellation of forces so precise it looks like a miracle. The impossible galaxies suggest that this cancellation might not have been perfect in the past. The bear woke up once, it can wake up again. We are sitting on a bomb with a faulty timer. We often speak of the Big Bang as a singularity, a point of infinite density. But if the universe had structure immediately, as Webb hints, then it wasn't a point. It was a chunk. A chunk of what? A chunk of a previous universe? This leads to loop quantum cosmology, which replaces the singularity with a bounce. The universe contracts, reaches a critical density, the chunk, and then bounces outward. In this model, the impossible galaxies are the first things to reform after the bounce, perhaps seeded by the memory of the previous universe. We are living in a recycled cosmos. The atoms in your hand have done this dance before. They have been crunched, bounced, and scattered an infinite number of times. Eternal recurrence is not a philosophy. It is a physical mechanism of a breathing universe. The Copernican principle states we are not special, but the rare Earth hypothesis argues we are. Webb's data supports rare Earth by showing how hostile the early universe was. To survive the epoch of universe breakers, with their intense UV radiation, supernovae, and black hole winds, is a statistical anomaly. Most planetary systems formed back then would have been sterilized. We are special because we arrived late. We arrived after the party was over and the house was cleaned up. Our mediocrity is our salvation. If we had been born in the golden age of galaxy formation, we would be dead. We are the children of the cosmic autumn, safe only because the summer heat has faded. The visual of gravitational lensing is one of Webb's greatest tools. Space-time acts as a magnifying glass. But lensing depends on the distribution of dark matter. The lenses Webb is finding are stronger than expected. The background galaxies are more warped, more magnified. This implies there is more dark matter in the clusters than our models predict. Or, gravity itself is stronger on these scales. If gravity is stronger, the ultimate fate of the universe shifts from big freeze to big crunch. The extra mass Webb is finding might be enough to stop the expansion eventually and pull everything back together. The universe breakers might be the anchors that eventually drag us all back into the fire. Let's speculate on white holes. General relativity allows for the opposite of a black hole, a region where nothing can enter, only exit. Some theories suggest the Big Bang was a white hole event. Webb's observation of sudden, massive material appearing out of nowhere, the rapid galaxy formation, mimics the signature of a white hole, matter spewing into our reality from elsewhere. If the impossible galaxies are fed by white holes, then our universe is an open system. We are being pumped full of matter from another dimension. This destroys the law of conservation of energy for our universe, but saves it for the multiverse. We are the drainage ditch for another universe's black hole. The Tully-Fisher relation connects a galaxy's mass to its rotation speed. It works for spiral galaxies today. We don't know if it works for the universe breakers. If these ancient galaxies rotate too fast, they break the relation. It would mean that the relationship between baryonic matter and dark matter evolves. Dark matter might condense or evaporate over eons. If dark matter is evaporating, then the gravity holding our galaxy together is slowly weakening. Stars will eventually drift away. The Milky Way will dissolve. We are slowly unbinding. The glue of the universe is drying out and flaking away. We must address the sociology of science. The panic is real. Young researchers are finding their PhD theses invalidated. Old professors are defending their life's work against the data. This human element matters because science is done by humans. We are biased. We want the standard model to work because it is beautiful. But Webb is ugly. It shows a messy, chaotic, rule-breaking universe. The paradigm shift described by Thomas Kuhn is happening now. We are in the revolutionary phase where the old guard is dying and the new truth is struggling to be born. It is a violent intellectual time. The universe breakers are breaking careers as well as theories. The look elsewhere effect is a statistical trap. If you look at enough places, you will find a miracle. Critics say Webb is just finding the miracles, but the density of miracles is too high. It's like winning the lottery every day for a week. It stops being luck and starts being a rigged game. The universe is rigged to produce structure. Why? Is there a teleological purpose? A goal? Science hates purpose, but the efficiency of early galaxy formation looks almost designed. It looks like an optimization algorithm running to maximize star production. If the universe is an algorithm, what is it trying to compute? The dark forest theory of the Fermi paradox suggests civilizations hide because the universe is full of predators. Webb's data on the violent early universe supports a predatory environment. If the first civilizations arose in the universe breakers, they were born in fire. They would be aggressive, survivalist, and paranoid. If they survived, they are the old ones. They might be watching us, the naive newcomers in the quiet era, wondering if we are worth eating, or if we are too small to bother. The silence of the sky is not peace. It is a hunter holding its breath. Let's talk about strange matter. Inside the super-dense cores of these early galaxies, pressures might have been high enough to crush protons into strange quarks. Strange matter is contagious. If it touches normal matter, it converts it into strange matter. A strange-lit particle drifting through space could turn a star or a planet into a lump of strange matter instantly. The violent collisions in the early universe could have produced factories of strangelets. Are they still out there? Drifting mines left over from the war of creation? If one hits the sun, the solar system ends. Not with a bang, but with a conversion. The CMB cold spot might be a supervoid, a region with almost no matter. Webb is helping us map the voids. Voids are expanding faster than clusters. They are the bubbles in the cosmic foam. As they expand, they squeeze the matter in between. We live in a filament, a squeezed wall between voids. We are being compressed by the emptiness. Eventually, the voids will merge. The filaments will snap. The universe will become one giant void with isolated islands of dead stars. The universe breakers were the last great stand of matter against the encroaching nothingness. The pareidolia of science. We see patterns where there are none, but the patterns Webb sees, spirals, bars, rings, are undeniable complex structures. Complexity usually requires time. Entropy requires time to be reversed locally. To see low-entropy complexity, a structured galaxy, at the beginning of time, violates the arrow of entropy. It implies the universe started with high complexity and is degrading. This is the winding down theory. We are not evolving into complexity. We are decaying from a perfect, complex beginning into a messy, simple end. We are the rot setting in on the perfect fruit of the Big Bang. The axis of time. Does time flow at the same speed everywhere? General relativity says no. Webb looks at the past. But does the past exist back there? Or is it a projection? The holographic principle says all the information of a 3D volume is encoded on a 2D surface. If the surface, the boundary of the universe, is growing, the resolution increases. The fuzzy early universe might be low-resolution data. Webb is trying to zoom in on pixels that haven't rendered yet. We are hitting the resolution limit of the hologram. The anomalies are compression artifacts. we must consider the observer, you and I. We are made of the elements forged in these impossible galaxies. The carbon in your DNA was cooked in a star that shouldn't have existed 13 billion years ago. We are the direct result of the broken physics. If the standard model were true, we wouldn't be here. We require the universe breakers to create the heavy elements fast enough for Earth to form. Our existence is the proof of the anomaly. We are the monsters. We are the impossible biology made of the impossible dust. The redshift might be quantized. Some controversial studies suggest redshift doesn't happen smoothly, but in jumps, steps. If true, the universe expands in clicks, not a slide. This would mean space-time is discrete, pixelated. Webb's precise measurements are testing this. If we find redshift quantization, we prove the matrix. Only a digital simulation moves in discrete steps. An analog reality is smooth. The universe breakers might be clustering at these specific redshift steps, revealing the grid lines of the simulation. We are looking for the scan lines on the cosmic monitor. The Great Attractor is pulling the Milky Way, but behind it is the Shapley supercluster. And behind that? Webb hints at even larger structures. The dipole repeller. We are being pushed away from a void and pulled towards a monster. The flow of the local universe is a river rushing towards a waterfall. We can't see the waterfall, it's behind the zone of avoidance, but we can feel the current speed up. The early universe structures suggest these currents were established at birth. We have been falling towards our doom since the first second of time. Dark fluid. A theory that dark matter and dark energy are the same substance, behaving differently at different scales. A liquid universe. Webb's data on galactic rotation curves in the early universe supports the idea that the fluid was more viscous back then. A thick, syrup-like cosmos. It explains the rapid formation. Stuff stuck together easier. But now the fluid has thinned. We are in the thin era. The physics of syrup do not apply to the physics of water. We are trying to swim in water using strokes designed for syrup. No wonder we are drowning. The zombie galaxy phenomenon, galaxies that stopped forming stars early, is a memento mori. It proves that galaxies can die young. What kills them? Quasar feedback. The central black hole wakes up, screams with radiation, and blows all the gas away. Suicide. The galaxy creates a monster that starves it. The Milky Way has a sleeping monster, Sagittarius A. If it wakes up, we become a zombie galaxy. The Webb data shows this happens frequently. It is the standard life cycle. We are just lucky our monster is currently napping. The cosmic dawn signal, the 21 centimeters line, is the holy grail. Radio telescopes are hunting it. Webb provides the visual counterpart. When we match the radio map to the Webb map, we will see the Swiss cheese structure of the universe. Bubbles of ionized light in a block of dark hydrogen. But if the holes are too big, as Webb suggests, the cheese crumbles. The structural integrity of the early universe models is failing. The Swiss cheese is actually mostly holes. The substance of reality is thinner than we hoped. Population 3 stars might have left black hole remnants that are everywhere. Machos, massive compact halo objects. If the dark matter halo is made of billions of dead black holes from the first generation, then we are surrounded by invisible graves. Every time we look at a patch of empty space, we are looking through a minefield of singularities. Webb's mass estimates force us to reconsider machos. The dark is not empty, it is crowded with the corpses of the first stars. The dipole anisotropy. The universe should look the same in opposite directions. It doesn't. One side is hotter/faster. Webb's deep fields in different directions will confirm this. If the universe is lopsided, it has a bias, a tilted table. Everything slides to one side. This implies an external force. Something outside the universe is tipping the table. A neighbor universe? A higher dimensional object? We are sliding towards the edge of the table, and we don't know what's on the floor. Superluminous supernovae. Exploding stars 100 times brighter than normal. Webb sees them in the early universe. They are the lighthouses of the Dark Ages. But their mechanism is pair instability. Matter and antimatter creation inside the star reduces pressure, causing collapse. It is a nuclear bomb triggered by quantum mechanics. The fact that these were common means the early universe was a quantum minefield, scaling quantum weirdness up to stellar sizes, a macroscopic quantum nightmare. The James Webb is a machine of gold and beryllium. It is the pinnacle of our species, and it is telling us that we are insignificant. There is a beautiful irony there. We spent $10 billion to buy a mirror that shows us our own irrelevance. But in that irrelevance, there is a challenge. If the universe is broken, can we fix the theory? Or are we cognitively limited? Are we monkeys trying to understand calculus? The crisis might not be in the stars, it might be in our brains. Eternal inflation. The idea that big bangs are happening all the time, everywhere. We are just in one bubble. Webb shows our bubble is weird. Maybe it's a failed bubble. A bubble that expanded too fast. A cancerous universe. Most universes might be quiet, slow, peaceful. Ours is the tumor. Fast, aggressive, consuming. It explains the violence. We are in a runaway pathology of space-time. The gene's mass is the critical mass for a gas cloud to collapse. In the early universe, the gene's mass was higher because the gas was hotter. This means only huge things could form. No small stars, no planets, just giants. This confirms the top-heavy universe. It means the scale of life has shrunk. We live in the era of the tiny. Tiny stars, tiny planets, tiny creatures. We are the miniature version of reality. The gigantic era is over. We missed the time of titans. Magnetic monopoles. Theoretical particles with only one magnetic pole. Predicted by grand unified theories. They should be heavy. They should be leftovers from the Big Bang. We haven't found them. Inflation was supposed to dilute them. But if inflation was broken, as the clumps suggest, monopoles should be here. Are the universe breakers powered by monopoles? A monopole star would look like a normal star but burn differently. We might be staring at them and not knowing it. The cosmic background neutrino flux. Webb can't see it, but its data implies it must be warped. Neutrinos travel through everything. If the early universe was dense, the neutrino background is shadowed by the monster galaxies. Future neutrino detectors might see the shadows of the universe breakers. A shadow on the dawn of time. It's a ghost story written in subatomic particles. Modified gravity. MOND is the dark horse. It says dark matter doesn't exist. Gravity just works differently at low accelerations. Webb's early galaxies, massive without enough dark matter, support MOND. If MOND is true, Einstein was wrong. Newton was wrong. We have to rewrite physics from 1687 onwards. It is a total reboot of science. The crisis is an opportunity to delete the system and start over. But are we brave enough to delete Einstein? The void phenomenon. Boots void. The great nothing. If the early universe was clumpier, the voids should be emptier. Webb suggests the contrast is higher. Extreme density versus extreme emptiness. The universe is segregating itself. Like oil and water. Matter is separating from the void. Eventually, the two will be totally distinct. We will live in a dense cluster surrounded by an infinite abyss of true nothingness. The island universe theory returns. Vacuum metastability. We mentioned the Higgs field. But what if the universe breakers triggered local vacuum decays that were stopped? Aborted bubbles, scars in the fabric of space-time, where the universe tried to end itself but failed. These scars would look like weird galaxies. Distorted. Wrong physics. Maybe the anomalies are the healed wounds of a suicide attempt by the cosmos. The time lag. We see the galaxy as it was, but we assume it evolved into something like the Milky Way. What if it didn't? What if it exploded? What if the universe breakers are a dead-end evolutionary branch? Extinct galaxies. We are looking at the dinosaurs of the cosmos. They didn't evolve into birds. They just died. The early universe was full of failed experiments. We are the one experiment that stuck. Cosmic strings. One-dimensional defects in space-time, like cracks in ice. They are massive. They can seed galaxies. If the universe breakers are strung along lines, it supports cosmic strings. A universe filled with invisible, razor-sharp whips of gravity. If a cosmic string passed through Earth, it would slice the planet in half cleanly. We haven't seen one yet. But the early structure suggests they were there. Are they still whipping around in the dark? The Big Ring, a structure of galaxies 1.3 billion light-years in diameter, recently discovered. Webb helps confirm the constituent galaxies. It violates the cosmological principle. It's too big to exist. It looks like a structure, a ring. Who builds a ring that big? Physics or something else? It triggers the artificial universe paranoia. A ring is a deliberate shape. Nature makes blobs. Intelligence makes rings. Final parsec problem. Supermassive black holes shouldn't merge. They should stall. But they do merge. Webb shows they grew fast, implying they merged fast. Something pushed them. A third black hole? Gas drag? The mechanics of the monster merger are unknown. We don't know how the monsters eat each other, we just know they get bigger. The ignorance is the scary part. We are watching Godzilla grow, and we don't know what he's eating. Entropic gravity. Gravity is not a force, but a side effect of entropy. Like heat. If this is true, gravity is an emergent phenomenon. It didn't exist at the Big Bang. It turned on later. This explains why the early universe looks different. Gravity hadn't booted up yet. We are watching the software of the universe load. The impossible galaxies are the glitches during the boot sequence. The James Webb is looking for the first light. But what if there was light before the light? Pre-Big Bang radiation. Penrose says we can see it. The concentric circles in the CMB web might find the galaxy counterparts, the scars of the previous eon. If we find a galaxy that matches a CMB scar, it is proof of the cycle. Proof that we are just the current tenants of an eternal apartment. Dark sirens. Gravitational wave events without light. Webb is trying to find the host galaxies. If we can't find them, it means the black holes were kicked out. Wandering black holes. Ejected from galaxies, roaming the intergalactic void. Invisible. Massive. Hungry. The universe breakers might have ejected billions of these wanderers. The space between galaxies is not empty. It is patrolled by invisible sharks. Panspermia. The theory that life came from space. If early galaxies made heavy elements and dust 13 billion years ago, and the universe was smaller, material could transfer easily. The early universe was a mixing pot. Life could have started in a universe breaker and been blown across the cosmos to seed Earth. We might be the immigrants from a dead galaxy. Aliens in our own home. The scale of the crisis, it's not just one paper, it's hundreds. It's a flood. The dam has burst. The Lambda CDM model is drowning. We are currently treading water. We need a new boat. A new Einstein. But the data is so weird, the new boat might have to be a submarine. We have to go deep into the weirdness to survive. Surface-level physics doesn't work anymore. Chronology protection conjecture. Hawking thought physics prevents time travel, but the time dilation in the dense early universe tests this. If time was warped enough, causality loops could form. Closed time-like curves. The impossible galaxies might be caught in time loops, reliving their birth forever. We are watching a broken record skipping at the start of the track. Mirror matter, a symmetrical copy of the standard model particles, only interacts via gravity. Webb's mass without light could be mirror stars. Stars made of mirror hydrogen. They burn, but release mirror light we can't see. We might be looking at a mirror galaxy, a ghost galaxy occupying the same space as a normal one, a shadow world right on top of us. The big snap. If the universe is a rubber band being stretched and the universe breakers are knots in the band, what happens when you pull too hard? The knots tighten, the band snaps. The structural failure of space-time. The anomalies are the stress fractures. We are hearing the cracking noise before the break. Cosmic boredom. The end state. But the early universe was anything but bored. It was frantic. Why did it slow down? What sedated the cosmos? Dark energy? Or did it just run out of the good fuel? We are running on fumes. The impossible galaxies burned the high-octane gas. We are left with the dregs. The universe is an engine that is slowly choking. As we approach the conclusion, we must look at the human cost. We are creatures who need a story. We need a beginning, a middle, and an end. Webb has stolen our beginning. It has blurred our middle. And it has threatened our end. We are lost in the narrative. And that is the true horror. Not the monsters in the dark, but the fact that we have lost the map that told us where the light was.